Hello, my name is Tatsumi from Oguchi Lab, and this is the explanation video for the poster presenting Masuda's master's thesis, Proposal for Braking Strategy to Avoid Rear-End Collisions of Leading Vehicles, considering following vehicle drivers. With the development of driving assistance systems and self-driving vehicles, it is expected to observe in the future fewer and fewer rear-end collisions. One way to reduce the risk of second-party rear-end collisions is to have leading vehicles braking in a relatively predictable pattern. This is the aim of implementing in vehicles with driving assistance systems braking strategies which consider the situation both in front and behind them. To search for the most appropriate braking strategy for the leading vehicle, experiments were conducted to see if and how various braking strategies affect following drivers. Those experiments were done in a driving simulator. 41 drivers followed a red car in several scenarios. Each run had a different cruising speed, either 50 or 30 km per hour. And the red car applied a different braking strategy. In this work, the new braking strategy is named Snap Zero. The first three braking strategies have quite self-explanatory names, but let's look at all of them in more details. With the braking strategy called abrupt to gradual, the car will pull the brakes abruptly and then release them a bit after 1 second until it comes to a stop. With the constant deceleration braking strategy, the car will reduce its speed linearly until it comes to a stop. The gradual to abrupt braking strategy is the opposite of the first one. For 1 second, the car brakes softly, then harder until it comes to a stop. Snap Zero braking strategy for the leading car would offer its passengers a smooth and comfortable ride without brutal change in speed. Now you can observe the difference between the four braking strategies. The following gray cars are only displayed for illustration. It is not reflecting the behavior of a driver that participated in the experiment. Nonetheless, you can see how the space gap can differ greatly depending on the braking strategy of the leading vehicle. Now that data has been collected from the driving simulator, behavior indicators are computed for each valid run. This means that runs where the following driver was too far behind the leading vehicle were rejected, the threshold being a time gap of 3 seconds, equivalent to a space gap of 42 meters at 50 km per hour or 25 meters at 30 km per hour. Several indicators for the driver's behavior were considered, but two were selected in the end. They are reaction time and minimal peak. Reaction time is quite common. It's the duration between the braking times of both vehicles. In other words, between the braking events and the driver's reaction. Peak is the positive or negative distance reflecting the final state of the space gap between both vehicles when they are decelerating. Each formula includes the stopping distance of both vehicles, the space gap, and if the follower is still cruising, the reaction distance. A positive pCould means that in that situation, a rear-end collision wouldn't occur. Conversely, a negative pCould means that vehicles collide. pCould is computed for each time, and by taking the minimal pCould, we can have an idea of how dangerous the run was, meaning how close we were to a rear-end collision. With these indicators, we can evaluate the 4 braking strategies, and then try to select the most appropriate one for the leading vehicles. It should have a low reaction time and a high minimal pCould value. From the overview of the 4 braking strategies, we may suppose that some are more dangerous than others, mainly depending on the evolution of the space gap. When all runs were taken, no strategy was giving significantly lower reaction time. By eliminating outliers and focusing on the runs where the space gap was longer than 12 meters when the leading vehicle started braking, 2 strategies had better results. These were abrupt to gradual and constant deceleration. Looking at minimal pCould values, different braking strategies were found for each average cruising speed, 50 and 30 km per hour, being respectively gradual to abrupt and constant deceleration. By doing this kind of analysis to cover all runs from the experiments, a general trend could be observed. It has been observed that abrupt to gradual braking strategy would make rear-end collisions less likely when the average cruising speed is high, with the space gap being long. When the space gap is shorter, constant deceleration is more adequate for low cruising speed and gradual to abrupt for high cruising speed. The proposed braking strategy, Snap Zero, did not have convincing results. Further work might be needed to refine this table by setting various cruising speeds, for instance. That's the end of this presentation. Thank you for watching.